And you guys are all on the internet. Okay. So looking at this, you're not taking us down. It's just giving the book props for the explanation of what we talked about yesterday, which is great. I don't know why this little thing's in the middle of my. Let's see if I. Okay, it's gone. All right. So straight out of the book, things that I've been talking to you about as far as what's going on behind the scenes, so that you have a better chance of memorization. Right here, cutouts from this paragraph. Hamiltonian path must pass through every vertex of a graph, not necessarily hitting every edge. Not important. Hitting every edge is called an Euler path. The difference is significant, going over that sentence right there. For example, this is a new one. The driver of a street sweeper picking up leaves, what would they have to do? Would they have to visit every house or hit every street? They'd have to hit every street. So they are concerned with an Euler path, all right, because every street must be swept, so they must hit every edge. On the other hand, here we go. Third from the bottom sentence here. Delivery truck driver with packages for homes in the same neighborhood must hit every house once and only once. Why would they go back? So that's a Hamiltonian path and or circuit going back to base. So again, I like that this stuff is said so that it really gives you a chance to understand this further, or actually have a better chance of memorization. Okay, so what I decided today, a little different than last year, not that you care. I'll show you another algorithm to do what we tried to do yesterday. Maximize or optimize, let's say optimize, a Hamiltonian path slash circuit, and then try to find, starting from your home, and then getting back to your home, visiting all the vertices or all the what your project's going to be, colleges, in an optimized manner, meaning the shortest possible distance. Put that Chromebook away again, sir! This is back-to-back movies. I had to tell you to do that. I know you're not doing math. You're doing something else. Bums. Okay, so what's great about this is, like I just shared as they're writing this down, there's only one test for this. For any graph, doing the cheapest link only gives you one result. Yesterday, the repetitive nearest neighbor algorithm, however many vertices, that's how many different tests you had to do. Now, I will do this. We're going to do an example of this. Then I'm going to do one more example of doing everything the last 2 days. And the reason is you should walk out of here feeling infinitely comfortable about your project that you're going to do. And your project is going to be, you are going to pick 5 colleges, and you are going to also have your home involved, because you're going to leave your home, visit the 5 colleges, and then come back to home. What we're going to try to do is optimize that trip so you get the shortest distance possible. Again, remember, these are approximate. The reason I use the word approximate, you may not necessarily get the most optimized trip using the cheapest link and or the repetitive nearest neighbor. At least we'll get some good ones. We'll get some that are better than better choices. The only way you could possibly get the best one is you find all scenarios and then find the best one. With 6 vertices, that's a lot of scenarios. We talked about that. 6 factorial possible scenarios. Way too much. If you had a computer, maybe. All right, so here's the cheapest link. Basically, you have to stay away from 2 things. And what's written in red up here is one of the 2 things. You select edges, but never make a vertex more than degree 2. It's very simple. If you make a vertex degree 3, that's like visiting a house, leaving the house, and then going back to the house if you're the UPS driver, because there's 3 vertices or 3 edges coming from that. That makes no sense. You deliver the package, you leave, you never want to come back. So that's number 1. Number 2 is down in this yellow writing. What are the acceptable edges when we do this? A, do not make a degree 3 vertex. B, do not close your circuit early. So here's what the cheapest link is. You have your freedom, step 1 in blue. You just pick the best, lowest edge first. Okay? Then you look anywhere else on your graph, and pick another acceptable edge that is the next lowest, keeping away from making a degree 3 vertex and also not completing a circuit early. And then you keep doing that. So you're not stuck with, staying in order like in the other one. You can go all over the graph and pick acceptable edges, trying to pick the smallest ones as you go. So that's what all this says right here. All right, I'll give you a second to write this further, and it is real easy. Okay, it took about 2 minutes for my computer to act appropriately again, right? About 2 minutes? Okay, so looking at this, I given the book props again. Cheapest link algorithm directs us to create a Hamiltonian circuit. So this just says the same thing that we just said, just to hammer down the point of what you have to do. Picking lowest cost edge that does not add a third edge to any vertex, hence degree 3, right? Over there. And also avoid completing a circuit, which is right here, before all your vertices are involved. Okay, so that's what we got to do. So spend a minute. All right, thanks, computer, for working. To make this graph. Odd choice as far as these long loops on the outside, but again, it just hammers the point that we don't have to follow all the rules and all the graphs don't have to look exactly the same. Keep in mind here, this is a connected graph, which means every vertex has an edge to every other vertex. There is no disconnections between two separate vertices. So every vertex connects directly to every other vertex. You want to keep note of the weights, get those weights in there, and then we'll do the only cheapest link algorithm. Then we're going to do one more example after this that emulates your college thing. Okay, game on. Now, I should have probably not had this sentence here, but that's all right. We can zoom this out. You see your own graph. Here's the first step. You should draw the vertices. Okay, and then we'll keep track what we do here. And then when we do the cheapest link algorithm, remember my subgraphs yesterday were not, meaning as I drew a line, I also put the math off to the side. The way this works, it's not necessarily in order. So I am going to label these. And when I pick edges, I'm going to put the weights on the edges that I pick. You didn't really have to do that with the nearest neighbor algorithm because we could keep track of it and write them as we go over here. What I want you to understand is the whole scheme of what just happened here. Pretend this is a UPS driver and we live at A. Or meaning the UPS driver's base is at A. So you're going to leave A, go to the other houses, and end up at A. But you don't have to start at A. What you do is look at this. What's the smallest number on the graph? What is it? It's 9. And, of course, you can pick that. That's an acceptable edge. Now, it just so happens that it did come from A to E. That was luck. Looking at the scheme of this, how this all works, it's all fine. What's the next smallest edge? Not 12. 11. Is this acceptable to pick 11? This is what I mean about how different this is. You're not stuck with, now I have to leave from E and go to one of the other. No. You just start picking the smallest sides in order as long as you can, as long as they are acceptable. All right, what's the next smallest side? What number is the smallest number left? So it's 12, and that's this crazy loop from here to here. Is this acceptable to draw this? Meaning, does this make any vertex have degree 3? Yes or no? No. Does it close a circuit too early? No. So that's an acceptable edge. All right, so now we're all good. We picked the first 3 smallest sides, and they were all acceptable, which is great. Now we might start running into problems. What's the next smallest number? Not 12. Not 14. 13. Can I pick this 13? Yes or no? What does that do for the first time? Creates a degree 3 edge. So I cannot do that one. What's the next smallest side? 14. And that goes here. Is this acceptable? Yes or no? No. Same reason. It creates a degree 3. Think of the spirit of the question. That means the UPS driver goes to C, leaves C, and then for some reason goes back to C later. No, that's not the spirit of a Hamiltonian circuit. What's the next one? 16. Can I do 16? Can I do this to this? Yes or no? We did this in both classes. At first we said yes, but what's the problem? You close the circuit, and actually what hasn't happened is B didn't get involved. So no, I cannot do that 16. I closed the circuit early. All right, so what's the next one? 17, can I do that one? No. What's the next one? Can I do 18? And actually, okay, man, some anger in that yes. Take it easy. All right, now, of course, we should have understood in the scheme of this what has to happen. And what has to happen is B has to get involved. So you may leave the question for a second and say, all right, wait a minute. I got to get B involved. There's only two acceptable ways to do that. E to B or D to B. And that's what's going to end up happening. And, of course, at the end of this, we have to connect D to B, right? So I don't have to keep doing this. The last connection has to close the circuit, so I'm stuck with this last edge, which I'm going to loop way out here, just so it's out of the way of that 12. And now, remember what I said. Regardless of where the first edge I picked started, we want to start from A and end at A because in the spirit of this question, I'm a UPS driver. So I start at A, and then you have a choice. I could start at A, and I could go either to C or to E, right? It doesn't matter. So I don't care. I'm going to go A to E, but then now I'm stuck. E to B, B to D, D to C, and then C all the way back to A. And then the order of that is A to E. Okay, so it's 9, 18, 28, right? 11, and then 12. And then you get that sum. Okay? Cheapest link, one test. You get one and only one different answer out of that. Okay, now, in the spirit of this, and unfortunately for online, I decided to do this anyway. I'll talk about it online, but we're going to do this on the board. What I will do is a snapshot of what we do on the board. I already got it from last hour about your college project. So, here's number one. Your college project. Pretend this is like what we have here. The first thing you're going to have to do, so as you're taking this down, these are still your notes, those that want pretty notes, you are going to have to look up from your house 5 different colleges. So your chart will be one more row and one more column. So you'll have your home, and then pretend you picked a college that was in San Fran. This is not Butte, it's Butte. Detroit, Salt Lake City, and LA, pretend. So it'll be a little bit bigger. You'll have 6 vertices, not 5. What you're going to have to do is look up all the distances from your house to each college and all the distances from each college to each college and put it in this chart format. Look at an example. Of course, you can't do this online, but I'm holding up a poster of someone that did an A work job last year. Look in the light. We have 2 different charts. I'll tell you what the second chart is. So that's what they had to do first. Okay? From that, we're going to make a graph out of it. And I'm going to do that on the board. I already have second hours snapshotted. I'll include them in these notes, those that are watching online. Then we're going to do what you have to do for your college project. We are going to do the repetitive nearest neighbor, which for your college project will be 6 tests because you have 6 vertices. This only has 5 vertices, so one less test. 5 cities only. And then you're also going to do the cheapest link, which is a 1 test. After all of those tests, you're going to pick the best scenario, the one that gets you to start from home, visit all the colleges, get back to home in the shortest distance, the optimized between the 7 tests that you'll have for your situation. And we'll talk about that more on Tuesday, but I thought this would be a good idea for what we're doing in class. And then you should, if you pay attention and have, good student, stuff, feel really good about the project. And all you have to do is worry about it looking good. So now I'm going to the board. We're going to do this all on the board, and then hopefully you can, when I put the snapshots, understand how in this one I'm going to have 5 repetitive nearest neighbor tests, starting from each individual vertex. That's where we get the 5 different ones. and then a snapshot of the one cheapest link. There will be repetition. There's not that many vertices, so some of these subgraphs will be the exact same. It's just the nature of the beast. Okay,